Okay. Up to this point today, we've reviewed all kinds of processes, all kinds of material, a large variety of kind of isolated, either generic or little individualized slices of a process. Okay, this is part of the customization process. We're going to focus on this a little bit. What I've been asked to do is to look specifically at one or two researched case studies that Custom Fit is focused on and give you the quick overview so you can see how the whole thing fits together as a complete process. So Custom Fit has focused on, depending on how you count, 5 to 7 different sorts of case studies, including motorcycle helmets, prostheses, motorcycle seats, jaw implants, knee implants, and toy seats. I'm going to choose a couple of these, go through them in a little bit of depth. If we start with the helmets, Jan Willem was kind enough earlier to explain why you want to customize a helmet so that it fits, so that it's comfortable, and so that it won't pull off when you get into an accident. We've already seen a demonstration of the nature of a helmet. Rapid manufacturing still has some limitations on what materials can be used. So you cannot produce all of the different parts of this helmet. The outer shell, this polystyrene, expanded polystyrene center, which actually provides the cushioning very easily with rapid manufacturing. So we've chosen to customize a liner that effectively fills in the gaps between where your head is and where a standard helmet fits. You've just seen the scanning process with the Mini-Man. You saw the little laser light as it comes down. Same concept. That gives us head scans. Again, Jan Willem in detail went through the software process of how it works. They take it, manipulate it, and they come up with, as you can see down below, you've got, this is the inner cap for the head, 5 customized inserts that then the actual hard shell of a helmet goes on the outside of. Once you have that shape, that liner, then you can start to play with it. Okay? We don't want it to be too heavy, so we can start to add all kinds of holes. This is our first generation helmet, customized helmet. These holes made it a lot lighter. It makes it a bit cooler. Then we said, fine, what do we have the freedom to do with this rapid manufacturing process that you can't do otherwise? So then we started to add, if you look at this side right here, there's actually hollow channels that you can put inside the helmet, a bit like conformal cooling for injection molding, conformal cooling for your helmet, so that as you're riding, that air circulates all through your hair. So although you have a helmet on and you're safe, you still get that wild and free feeling that so many motorcyclists enjoy. Once the design is finished, before it goes to production, you need to be able to test it. Now, testing a motorcycle helmet, as we've already discussed, as you do these layer-based processes, the material properties are not the same in every direction, and isotropic. So, as part of the custom fit process or project, we've developed specific FEA tools that allow us to go through and virtually analyze how the part performs with anisotropic properties. To my knowledge, that is the first FEA analysis on multiple shells. You can see here there's multiple parts, how they are interacting, that is a non-isotropic material. Okay? So we're fairly pleased with that. We're proud of that. I think that's been a nice innovation that the Custom Fit project has allowed us to come up with. Once we're happy with it, then it goes through one of these new printing processes. We've been using SLS while this is being developed. And we end up with an insert that looks like that. I've pulled the soft liner out of this helmet. I'm holding in my hand a customized helmet. If you look inside, I'll pass this around in just a second. If you look inside it, see if that turns on. There we go. You can see the different holes. You can see this is the customized liner. You can feel it. It's got places cut out for the ears. This is customized for one man. Okay? Only he can wear it. Part of the disadvantage of it is that only he can evaluate it as well. I'm going to start to pass this around.
That's quite a thick wall section there. We should emphasise that on other honeycombs, that one there is a little thinner. So the wall section on that honeycomb is about 2.5 mil. And we did go all the way down to 1 millimetre, just to try and get the weight down, not the lightest of things at the moment.
What Dave's trying to emphasize is this is our first generation. The current generation, which I'll show you a picture of in a second, is still being tested, so I don't actually have it here in my hand because it's in Italy. Again, an image of what's being passed around. Let me show you what the results look like on first generation. We took some pressure mapping equipment, put it inside the helmet. A standard helmet, according to the correct size that you could buy off the shelf, gives a fairly high pressure area on this particular individual, particularly at the forehead. If you go down a size in helmet, just to emphasize what happens, you can see again you're getting pressure on the forehead, which is that bright red spot, and then all across the back. We're very pleased to say that is our result on a helmet that's being passed around. You've got a much more even distribution of the pressure, giving greater comfort and allowing people really to have a much safer ride. There's still more to do. We are still customizing. We're working on the mesh that's being passed around with the hexagonal pattern on that one is kind of it's a normal spread. We're starting to manipulate the hexagons to give it a little bit more kind of graded functionality in its structure and performance. Again, we're taking away parts of that helmet that aren't necessarily doing very much, making it lighter, cheaper to produce, etc. I think that it's very clear when you've got a surface like a head, which is relatively hard, and a helmet. You can scan those two items, put them together, no problem. What happens when you start to look at things that change shape, particularly during their dynamic use? So if you go to things like seats, your posterior section deforms every time you sit down. The other part, the seat itself, also deforms. So how do you deal with that in a reverse engineering context? Any ideas? Dave actually gave us the answer a little earlier by using the pressure mapping equipment. Ducati put a survey up on their website and said, how many of you experience discomfort on long rides? And we have back 92%. 81% of those of the people surveyed said they would love a customized seat. The current seat consists of a rigid, hard bottom that's injection molded, and then they've got, forgive the crisscross the grid on that, but it's a foam section that goes inside it, and then they've got a cover on it that they call the Sky, which is leather-like. What we're doing is eliminating this padding. Actually, we're not eliminating it, we're replacing it with a rapid manufactured one. The only catch is polyurethanes are a little hard to rapid manufacture. So you've got to go with a slightly different material and create a structure inside it to mimic that soft feel as you ride. The process, as with all of the processes, is gather information about the customer, either through measurement and, in this case, pressure mapping. So you can see right here effectively a bum print, for lack of a better word, a pressure map of someone sitting on that seat. Now, the third bit, subjective feelings. I'd like you to raise your hands in this room. How many of you like a hard pillow to sleep on? Okay, now put your hands down. How many of you like a relatively soft pillow to sleep on? Good. You know that you have a preference. You have some frame of reference for that. IBV have worked out a fairly sophisticated system